Today we're going to do a short video on cross-channel phase in SKF's Microlog dBX. So there have been a lot of questions about this, so we thought a video would be nice to explain it. So the first thing I'm going to do is go into the analyzer module. So I've just got the dBX's screen displayed here in the video. So I have a rotor kit that you can probably hear in the background turning. That rotor kit has two accelerometers in the horizontal direction, two in the vertical direction. Then I also have a speed pickup on it. But I'm not using that speed pickup because it's cross-channel phase. We're looking at phase comparison from one channel to the other. The rotor kit has a pretty strong, relatively strong imbalance in it. So the first thing I want to show you is the configuration. The analyzer setup, like I said, I have 4 accelerometers and a tach. For the channel setup, I have, they're all ICP accelerometers, standard there. Again, standard on the engineering units. And finally, if we look at the FFT settings, I have time waveform, complex FFT, auto spectrum, and cross spectrum. For the purposes of cross-channel phase, then really the only one that I need to have is either the cross spectrum or the complex spectrum. I'll be able to get my phase information for comparison out of that. But I've got the others, and we'll take a look at them. Just going to show you what's going on in those plots. So for the frequency, it's turning at 25 Hertz, roughly 1500 RPM, so a little bit faster than that. So I've just got my frequency band set to 200 Hertz with 800 lines. For the averaging, it's not strictly speaking necessary to do averaging, but I've got 5 averages with a lot of overlap there to speed up the process. Then for the trigger, for the averaging, the triggers are trigger channel is necessary. And then I'm not doing anything with the waterfall. So we can go ahead and hit OK there, and we'll collect some data. Rotor kit's already running, so let's open up some of these plots and show you what's going on. First one we'll look at is the cross spectrum, and then we have, it actually just finished taking data. Sorry, the complex spectrum. And then I have the cross spectrum down here. We'll rearrange how that displays. And then one thing I want to point out is that over here on the left I have my complex spectrum. First thing I want to do, I'm just showing you the FFT. That's the default plot that comes up. If I go and change my plot over to what the dBX is calling a Baudet plot, then we'll see the phase down at the bottom of below the FFT. So one thing to note is we have a pretty clear 1x signal. There is imbalance in this rotor kit, but I can do phase at any of these frequencies. I just need to have a clear vibration signal that it can anchor on to get that phase. So here I'm looking at twice running speed, so there's phase information there as well. If we go back out and kind of focus on the 1x though, which is really what we're probably most often going to be looking at, I'm going to zoom in on that range and both of these plots so we can see what the amplitude and phase are at those areas at 1 times, which again is roughly about 26 Hertz, a little over 1500 RPM. So if we look at the phase, it's cross-channel phase. Again, I'm not using the speed. It's just comparing these signals. It's looking at the real and imaginary portion of the complex FFT and the cross FFT, using the real portion, well, doing the root sum square of those two values at each individual bin to give you the amplitude in the FFT, which is what we usually are interested in. But I can also do the arctan of the ratio of those two values to get the phase, and that's what's plotted down below. So the 2 plots that we have there, like I said, either one just depends on whether I want to see the amplitude of the FFT or whether I want to see the cross relationship between the 2 channels. So that's what we're seeing on the right is the higher channels with respect to channel 1. On the left we see all 4 channels individually. So on the left, if I'm going to use that, I've got to actually do a little bit of math to figure out what the relative phase is. So for example, if we look at channel 1, it calculates the phase at 93, channel 2, 249, then channel 3 looks like 37, and then 224. So if we want to do that math, then, and actually I think that's an 87, because once I come over here, 93 to 249, if I do that math, I have to kind of roll around the 360 degrees. That gives me 203 degrees. It's a little easier with the 93 to 87 degrees, because that's just going to be a 5.4 degree phase change, 93 minus 87. And then 93 minus 224, again I have to roll around, and that gives me a phase of 228. So again, just really both of these plots have the phase information in it, and it's a question of whether you want to do the math yourself. So the other plots that we have that I wanted to show you was the time waveform. If I zoom in, kind of see what's going on here, you can see that, and we saw it in the phase data itself, that we have basically 180 degrees between the horizontal and vertical plots, vibration, and 0 degrees between the horizontal and the vertical. And that is really just a function of the fact that my rotor is just sitting on the tabletop, and it's just hopping up and down. So it's got a little bit of an odd vibration signature for a unbalanced situation. And the other thing that I was going to show you was just showing you the tag that tells me that it is at 1570 RPM, though again I'm not actually using that for a phase. And then if we look at the trend, then you can see that, as I said, the horizontals are a little bit lower amplitude than the verticals, and so that gives us that, helps kind of contribute to the 180 degree phase difference, the fact that it, like I said, it's just hopping up and down. So that is a quick view of cross-channel phase in the Microlog Analyzer dBX. Thanks for watching.